Okay, hello. One of the things that you're probably anticipating about physics is that there's a really strong connection between physics and math. And this is certainly true, but I don't want you to worry so much about it and let the math get in the way of the physics. So this little tutorial is going to give you some pointers about formulas in math that you should find useful throughout the course. And we'll start off with a couple of statements here. It's pretty much true that physicists work to find the relationships between different quantities. That's really what a lot of physics work boils down to, is figuring out how one quantity is related to another. An equation is a mathematical sentence that describes the relationship between quantities. And so oftentimes in physics, we'll be using equations and formulas to represent the relationships between different quantities. Sometimes you will be given the equation and asked to use it, and sometimes you'll actually be asked to come up with the equation on your own based on some data or some information. Now, before we go any further, let's say a couple things about equations, because what you learn about in math class is slightly different than what we're going to learn about in physics. The equal sign has two very distinct meanings. It can mean exactly the same as. So for example, we can say that 12 inches equals 1 foot. And that means that they're exactly 12 inches in 1 foot. This is the way that your math teachers usually use the equal sign, is to say that the left side of the equation is exactly equal to, or the same as, the right side. However, in physics, the equal sign can mean something else. And you can assume that it means something like to say it is caused by. So for example, we can say that the acceleration of an object is caused by a net force acting on a certain mass. And the equation acceleration equals net force divided by mass is a mathematical way of saying that. Okay, so there's a subtle difference there, and most of the equations in physics you can interpret in that sort of a way. Let's say a couple things about formulas and about what goes into a formula. One of the things to understand is that in a relationship, we're talking about quantities that have dimensions. So let's think about a couple things here. The statement is that dimensions follow formulas. So for example, we know this first equation stands for velocity equals displacement divided by time. That's a very basic formula for motion. The dimensions of that relationship would be the dimensions of length over time, because displacement is a length and time is time. So the dimensions of velocity are always length over time. Consider the second equation. Hopefully you recognize this one. Area equals length times width, say the area of a rectangle. The dimensions of area would be expressed as length squared, because you're essentially taking two lengths and multiplying them to get an area. The last equation is one which you use in chemistry. That symbol there is called a rho, but it's the symbol for density. And density is equal to mass divided by volume. And in the case of this last quantity, the dimensions would be the dimensions of mass divided by the dimensions of length cubed. And if you think about it, all volumes can be expressed as length cubed. If you think about calculating the volume of a box, or even the volume of a sphere or a cylinder, you're always essentially multiplying three lengths. So the dimensions of formulas really don't change. Each formula will have specific dimensions which remain the same forever. In contrast to this, we have units. And students sometimes confuse units with dimensions, but they're not the same thing. So let's just come back to the first formula that we use, velocity equals displacement over time. The dimensions of that formula are always length over time. However, the units can be many different things, and the units simply have to follow the formula. So you can have units of meters per second, miles per hour, kilometers per day, inches per year, whatever you'd like. There are probably thousands of things that you could come up with. And notice that in each case, the units are always units of length divided by units of time. Okay, so the units always follow the formulas. Here's a couple of examples of what we mean by units following formulas. If you have a formula for area, length times width equals area, obviously you multiply a length of 5 centimeters times a width of 6 centimeters. 5 times 6 gives you 30. But don't forget to also multiply the units. So centimeters times centimeters will give you centimeters squared. And those are the appropriate units for area. Similarly, for density, mass divided by volume equals density. If you divide 15 grams by 3 milliliters, you get 5 grams per milliliter. Notice that the grams per milliliter come from the formula for density. And I'll put 2 more up here. Velocity times time equals displacement. Note that seconds cancel, leaving you with meters for displacement. And the last example is kind of a strange one, change in velocity divided by time. If you divide a change in velocity of 10 kilometers per hour by 5 seconds, you get 2 kilometers per hour times seconds. Nothing cancels here. And these kind of strange units of length divided by time again are actually the units which are used for acceleration, which we'll be learning about soon in this class. So the basic idea here is that the units follow the formulas. And it's always a good idea to write the units in as you're doing a problem. I'll say a couple of things about rearranging formulas. This is a math skill that hopefully you've been using in your math classes for a long time. We know that if you have a formula like velocity equals displacement divided by time, we know that you can rearrange it to solve for displacement and to solve it for time. And it's a matter of cross-multiplying or cross-dividing to do those things. Where students sometimes get into trouble is rearranging more complicated formulas. In physics, we have a lot of formulas that involve squares and square roots. Here's an example. This formula, T equals 2 pi times the quantity m divided by k to the 1/2 power. This is the formula for the period of a mass spring system that's oscillating. Now, we don't really need to know that. If I were to ask you to solve for m, to isolate m in this equation, you have to know which steps to take. The first thing you would do would be to cross-divide both sides of the equation by the quantity 2 pi. That leaves you with m divided by k to the 1/2 power on the right side. The next step that you do is to square both sides of that equation, and that will eliminate the 1/2 exponent here. And it will introduce a square on the left side. So now you're left with t over 2 pi quantity squared equals m over k. The last thing you would do would be to cross-multiply by k so that you can isolate m. So you can probably imagine that a common mistake is for students to immediately square both sides of the equation and then divide by 2 pi. This, of course, is not correct, and you'll get the wrong relationship at the end. So be careful with your steps and write them out if you have to. Another very common formula is an inverse square law. This is a famous one in physics. It's the universal gravitational formula. F stands for force, G is a constant, m1 and m2 are masses, and r is a distance that gets squared. I'm going to leave this up to you to solve for m1, in other words, isolate m1. Okay, and if you did it correctly, you'll get this as your answer. Notice that you did not need to take a square root at all when you solve for m1, because you're simply cross-multiplying both sides of the equation by r squared. However, if I ask you to solve for r, which is the distance, now you have to take a square root. So try that out. And the final answer that you get will look like this, but notice that everything inside of the curly brackets is square rooted. So you have to be careful with your steps. And the only way to do that is to write down step by step and follow your steps carefully. The last thing in this tutorial that I'll mention, and only briefly, is the proper use of scientific notation. Scientific notation is important because It's a very clear way of showing the precision of your measurements. In other words, how many significant figures you have. If we have a velocity of 1.50 times 10 to the 5th meters per second, we understand right away that there are 3 significant digits in that measurement, because there are 3 digits that are written up front. It's also a very big number. If you write this out in decimal form, it's equivalent to 150,000 meters per second. When you deal with this number in equations, sometimes you'll have to add things to it. You can try this on your calculator, but notice that if you simply add 1,000 to that number, you're not changing the exponent. You're simply changing the prefactor. So that would become 151,000 meters per second. By contrast, if you multiply by 1,000, or if you divide by 1,000, you are directly changing the exponent by either adding 3, so when you multiply by 1,000, 10 to the 5th becomes 10 to the 8th, or by subtracting 3 when you divide by 1,000. 10 to the 5th becomes 10 squared. So notice that multiplying or dividing by 10 changes the exponent. And maybe try that on your calculators. And we'll finish this tutorial with just a quick calculation that I recommend that you try on your calculator. We could ask the question, how many times faster is the speed of light than the speed that we just used in our example? So the speed of light in a vacuum is a famous number. It's 3 times 10 to the 8th meters per second. Pretty fast, huh? It even has a special symbol in physics. It's a lowercase c. So if I ask you to calculate the ratio of that speed divided by the velocity that we used previously, 1.5 times 10 to the 5th, you should be able to do that. Now, a quick thing to do here is, one quick way to do it would be to divide the prefactors first. So 3 divided by 1.5. That, of course, gives you 2. You would then follow by dealing with the powers of 10, and since you're dividing by 10 to the 5th, you're really subtracting 5. So this is 10 to the 8th minus 5. In other words, it's 10 to the 3rd. So your final answer here would be 2 times 10 to the 3rd, or 2,000 times faster. Okay, I would recommend that you try that on your calculator and make sure that you can do it. Some calculators require parentheses, some do not. You need to know your calculator so you can do the math correctly in labs and on tests. So that wraps up our tutorial on formulas in math. Hopefully it gives you an idea of the types of skills that you'll be needing to use throughout the year. And hopefully these skills are already pretty natural to you. But like anything, it's going to take some practice, and you'll be confident quite soon. Okay, bye-bye.